So thanks to all for the organizers for having me. What I want to talk about is a blisteringly fast overview of work that we've been doing on brain architectures. In particular, I'm talking about brains and not just neurons. Just for those of you who have an opinion on the matter. Let's see, can we see the arrow? Yeah, good, sweet. Our aims are to make contact, make anchors both at the bottom from biological derivation and at the top to actually perform algorithms of interest, and I'll show you examples of all of those. Our approach is, there was a lot of talk yesterday in the afternoon group session about how can you possibly do this? We don't know enough about brain. We can't just take algorithms and try to reduce them to brain-like things that they don't turn out that way. So what do? What we try and do is iterate. We start with analyses that actually many of which are at very low levels down to the ion channel level. And we build simulations of them, we run them, we observe them, we try to see what they do. We give them physiologically reasonable, and I'll tell you what I mean by reasonable inputs, and we try to observe their behaviors, and we hope, and it's all on hope. We hope that we see regular kinds of behaviors that we can understand as algorithms. We turn those things into algorithms, then we do the appropriate responsible computation thing, which is look for families of algorithms that are related to these, do computational complexity analyses, and from that we go two directions. One is we go back to biology, we go to experiments and analyses, and the other is that we extrapolate up to the level of elementary operations and how they compose. And finally, we start to loop back to our biological analyses, our simulations, and our algorithmic hypotheses. That's going to be the recurring theme throughout the talk. The aim throughout is to identify principles, and every once in a while I'm going to pop up a box of this kind that says principle here, and try to argue that some of the things that we see over and over again are also things that we will have seen in many of the other talks that may be identifiable as principles for how we should be proceeding. I'm going to start by giving the sort of the punchline end point of the entire talk, just so that I can then walk you through it and bring you back full circle to it. The punchline is we're working on brain circuits. Brain circuits compute grammars, and by grammars I mean specific, simple, specific mathematical thing, which I'll show you. Grammars encode time and structure relations, and we go from low-level perceptual encoding using very real neural elements to up to hierarchical construction of what we can literally call logic statements, and I'll give you examples of both. And this seems crazy. I think Todd Hilton was the one who said in his very own slides, Todd is nuts. It's possible that I'm nuts as well, but I think not. And in fact, what we'll do is try to step you through these things from the bottom so that we can make these arguments. I'll give you examples of current unsupervised, supervised, and partially supervised learning on very large data sets, especially including time-varying things. Almost all these things care about time. So we're going to look at sound and sound over time. We're going to look at video. We're going to look at motion. We're going to look at some motor behaviors. We're going to look at interleaved perception and action. And the proposal is that we can go from raw data up to higher-level constructs. Outline of the talk. I'm going to whiz through things like what the brain circuits are, how we build them into algorithms, how these things can be treated mathematically as grammars, and I'll show you some of the formal treatments. What these things then build, what kinds of representations they build internally, and I'll call them representations. And then finally, I'll, after I zoom through some of this stuff, I'm going to stop, change gears, and start to talk about what they do and give you some examples. Everything that I show you, I think there might be some exceptions, but I think everything I show you appears in publications, and I'll point out the publications. Finally, I'll take you to hardware implementations, why I think hardware desperately matters, and how it is that we're addressing that. Okay, start with brain circuits. Our brains didn't come out of nowhere. There's an evolutionary history to them. These things are constraining. Where these things came from, there's only certain kinds of constructs that occur in brains. Those constructs recur over and over again, and we use those to greatly constrain, constraints are our friends, to greatly constrain the set of things, the set of algorithms that we can derive. On the other hand, not everything is cortex, and certainly not everything is just neurons or neuron soup, as we like to derogate it, but rather these things occur in architectures, and those architectures have recognizable layouts. So the circuit components are cells and local circuits, and the components of these things, these have interesting characteristics. Among other things, they're probabilistic. They're unbelievably slow, many orders of magnitude slower than any self-respecting engineer would ever build anything out of, and yet somehow they're doing things that we can't do. That's a very useful constraint. They're sparse. Yes, got it. They're low precision. And so I'm bringing a bunch of constraints to the table, and I'm going to use those as design constraints, and we're going to come back to them over and over again. But there are different cell types in different architectures, and each of those different circuit designs, thalamocortical ones, striatal ones, corticostriatal ones, hippocampal, amygdala ones, cortico-amygdala loops, each of those is a distinct kind of architecture that does a different thing, and they're embedded into an integrated architecture on this scare slide. I'm going to simplify this guy, which is still a little bit complicated, to something that has a posterior and an anterior cortical component and a loop, if you see, from anterior cortex down to striatum, pallidum, and back up to cortex. And then I'm going to suggest in the first of the constraining principles that I'm going to introduce that loop, this loop, recurs. There's one of these dedicated to vision in your brain. There's one of these dedicated to sound. There's one of these dedicated to touch. And there's many more of these that recur over and over again that are dedicated to things that we don't even have real names for. This is arguably the architecture of mammals, and certainly the architecture of human brain. This repeating set of cortical and subcortical sub-architectures is the thing that happens over and over again. Not even controversial to say so. And the anatomies of these things are extremely well worked out, have been for some time. And so what we're going to try and do is focus our attention on how do those things interact, how do they play with each other in such a way as to give individual algorithms and composite algorithms. Here's another constraint. The components of brain scale allometrically. So here is the size of components within your brain, neocortex, diencephalon, midbrain, la la la. Here is the overall size of your brain. And what you see is, these are just the primates. What you see is that these guys are unbelievably predictable. If you just look at the primate brain and you just know the size, the overall size of the brain, boom, you know the size of every component in that brain. That's shocking. It should be shocking. The reason it's shocking is because where's evolutionary pressure? Where is the differential pressure to make some of these things different sizes, some of these things different connectivity patterns? It's not there. Worst of all, there's you. You are smack on that curve, and if you simply took a chimp brain and scaled it up to the size of a human brain, and again, this is not even a highly controversial thing. There are dissenting views, but there are a substantial number of publications, not from us, from lots of neuroscientists and evolutionary scientists who show that these measurements come out the same way over and over again. We are on that curve. It's not that there's been a world of evolutionary specialization for us, but rather we have the brains that our ancestors had, and that's a constraint. It begs the question, how come we can stand up at podiums and do things like that other animals can't do, like sit still and be quiet, right? Impressive things. Go to the zoo and check that out. It's not happening that way. Do we get qualitative differences from quantitative brain size changes? I'm going to suggest that we indeed do, and therefore one of the constraints on us is what kinds of algorithms, what kinds of computational devices can you get new kinds of operations out of just by making it bigger or making more copies of it. And there aren't a lot of those, but they certainly do exist, and we'll see some examples. So components scale allometrically, by which I mean they're on that curve. Okay, let's jump now to algorithms from these circuits. I'll start with thalamicortical loops because it seems to be everybody's favorite in the room. Here is a very, very simplified little diagram of thalamicortical. Here's the two key types of thalamic nuclei, specific and nonspecific. Here are their projections up to superficial layers and back down. And what I'm now going to do is I'm going to take one of these and I'm going to split it into two parts. Oh, and by the way, we are using a world of detailed anatomical pathways and physiological data when we build these models. But what I'm going to do is cartoon them for you. Here are the two starting cartoons. This and this, the two things, are the exact same diagram. All I've done is highlight parts of one versus parts of the other. And what I'm going to do now is take you through, because I'm hypothesizing that they do somewhat different things and then they integrate with each other. I'm going to take you through this so-called core loop that's using this thalamic input primarily, and then I'm going to take you through this one that's using the matrix thalamic structure primarily, and then we'll integrate the two of them. Again, in cartoons. Here's the core loop. Inputs come in right here. They go up to the middle layer, layer 4. They go up to the superficial layer where we've got a inhibitory feedback thing. They go down to layer 5, and layer 6, and layer 6 projects back to not just to the input structure, but also to the nucleus reticularis, this inhibitory thing that covers the entire surface of the thalamus and inhibits the stuff topographically that's right under it. And for this little cartoon, I'm going to just focus on static objects. As I said, most of our work is going to be on moving objects, but I'm going to start by focusing on static ones, by which I mean you're looking at the screen, you're looking at my face, you're looking at some object, a flower in this case. And here's what happens. Input comes in, goes up here, we get, in almost everybody's hands in this room, we get some kind of clustering algorithm coming out of lateral inhibition. And now we subtract that category from the input. Here's the subtraction step. And the input's still there. You're still looking at it. What happens? It comes back up, goes through again, and you get sub-clustering. You iterate, and what you get is some level of recognition, some sub-level. Here's things that have large petals versus thin petals. Here's ones that are white versus yellow. And what you're getting, literally reading out from that loop, you're looking at a static object, you're reading out from that loop over time. So you're getting a cortical response. Boom, another cortical response. Boom, another cortical response, because you're subtracting something from it each time. That series of subtractions is reading out category, subcategory, sub-subcategory. So that's a quick cartoon of something that has been, there's been, I don't know how many publications that suggest this, again, starting all the way down at the level of extremely low-level biological components that actually make sense, and then going up through simulation, going up to the algorithm level, and hypothesizing that this may be something of the kind that those circuits may be doing. One of the things that it says, psychologically if you will, that recognition is nothing more than categorization. It's just sub-categorization. So you look at something enough, you're going to get sub-categorization. It also suggests that if you just glance at something, you're going to get categorization but not sub-categorization. We'll show some data like that. Another one of these little principles, we're getting high precision computation, that is recognition of things, from these low precision components. And the reason we're getting that is because we're iterating. We're using the same components over and over again in a loop, and that iterative reuse of them is giving us successively more and more precision just by reusing them. Again, being good computer scientists, which is what I am, we turn these into algorithms, and we are just doing incredible violence to the biology, throwing it away and trying to understand it algorithmically speaking, and trying to understand what it costs. Because computational complexity, if you have something that is an extremely costly algorithm, it's not going to scale. If it's not going to scale, it's not what the brain's doing. And those of you who want to dispute it, we'll talk. But I do suggest to you that you really, really want something that scales. And so we're constantly looking at time and space complexity. These things happen to have very good space costs and astounding time costs, especially when they're implemented in appropriate parallel hardware, which of course in brains they are, and which I'll talk at the end of the talk about how we're doing that with some of our hardware designs. Okay, that was the core loop. Here comes the matrix loop. Now what we're getting is, this is the matrix thalamic nucleus, not the core one. And now the input to this is not coming from the outside world. It's only coming from feedback, layer 5 feedback, from other thalamic areas down to this thalamic thing and back up, not to layer 4, but to a huge, huge input, at least as large, larger in most cases than the layer 4 input. Very large input that goes up to layer 1, which is making contact with these same superficial cells. So now, what do we get? Now let's look at time-varying inputs. So here's a little speech sound. I forget what this says. Bird, I think. Bird. And here's what you're getting is successive. So you think that you're hearing things continuously, just like you think that you're seeing things continuously. You're not. That's why movies work. The reason that you can look at a snapshot, a succession of snapshots and think that it's a continuously moving movie is because your brain has a time window for looking at those inputs, and it is putting them weaving them together successively. The same thing is going on with audition. Again, not a controversial claim. This is what happens. There's loads of neuroscience that goes with this. So we're getting successive time windows, bum, 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 left to right, and now what we're learning, look, the first one comes in, it goes up to the top level, becomes a category, just like that thing that we saw a minute ago, but then it's feeding down to this, and feedback is occurring. We can think of this as a simple kind of hashing. It's very, very simple. It's just doing an orthogonalization. It's spreading these things out. So even things that are very, very similar have different codes down in this thalamic nucleus. And so now what we're getting is a code that tells us, oh, this thing came in, and now the first one, A, feeds back as the second one, B, is coming in. And we get the combination, A followed by B. Then we get B followed by C, and we're chaining those things. And as we'll see, we're doing hierarchical chaining, and we're doing sequences of sequences. But again, because these things are categorizing, we're actually getting sequences of categories of sequences of categories. And I'll show you what those look like. Again, we turn these into algorithms. We can show that they scale very nicely. In fact, they scale linearly. So the more tissue that you throw at it, the more synapses that you throw at it, the more sequences of this kind that you can store linearly, which is nice because it means you can make very large versions of it. Okay, now we've got these two things combined. And by the way, I left out striatum, basal ganglia, the hippocampus and corticohippocampal loops, the amygdala. There's a world of literature on these, some of it from us. We borrow absolutely wherever we can, sometimes with attribution. And we now combine these things into a group of a set of algorithms. This is just a summary slide of these thalamocortical algorithms. I told you clustering, I told you hierarchies, sequences, and we're going to call this our bottom-up derived proposed instruction set. These are the pieces that these simple simulations are telling us we have to work with, and the question is, what the heck do they do if they're interacting together, and if they're working in an architecture? So those algorithms are integrated into this larger architecture, this cortical subcortical architecture, and I'm going to focus just on categories and sequences, but we'll expand that in a moment. Again, the output of this structure is being fed in as the input to the next structure. And the output of this is fed into the input to the next. You're getting sequences of categories of sequences of categories. Those are grammars formally, and I'll treat them that way in a moment. So we've now got a shared data structure across all these, and the shared data structure is these nested sequences of categories. What kinds of representations does this build? We bring in, for instance, pictures. Early areas are just doing simple features that they're extracting. Downstream, we get a specialist, if you will, that's looking at this kind of thing versus this kind of thing. The outputs of these become inputs to downstream specializations, and what you get are specialists downstream that are being constructed by fan out and fan in from the early structures. This is just what you see when you look at, well, if you look at single units in when you're allowed to, or if you look at fMRI in humans. And what you get are distributed, sparse patterns of representations that we can identify, that the field can identify, and we can tell an object just by the representation that shows up even in something as coarse-grained as an fMRI routine. Neuroimaging data, therefore, is helping us constrain representation. And all of these, by the way, are just grammars. They're learned grammatical relations among these components. That includes multiple kinds of relations. ISAs are the ones I focused on, but I'm going to show you examples of followed by, sequence, composed of. These grow in a principled fashion. So if we just do the thing that we're used to with grammars, which is pretend that there are word inputs instead of feature inputs, we'll talk about that later, but you've got sentences, you get abstractions from those. If Bill and John both hit Mary, then A hit C. We can do formalisms on these, and all you have to do is go a few steps downstream. You will have representations that correspond to these abstractions. So we now have a candidate. We have these grammars, and it's easy to show, it's been shown many times, that in grammars, quantitative changes do make qualitative changes. You can get very different behaviors out of these things, grammars, just by adding one statement to an existing body of grammars, which is interesting because it gives it some of the characteristics that we want, and of course we didn't choose it for that. We chose it because that's what these thalamocortical loops seem to be saying. The kinds of categories, by the way, that it creates, some of them are similarity-based categories, we'll see some examples, but some of them are position-based categories, that is, things that occur in certain contexts. So here's a bunch of things that occur in certain places in a sentence, if you will, WH words, that kind of thing. I'm going to just skip through this. There's an overview of this algorithm that I can point you to publications, how we step through a loop that is trying to find us from features, building grammars, and then trying to apply those back to the inputs. Relations. So I want to now take that, bring it back to something quite familiar. So what it's doing is it's building grammars. But with grammars, you could do a lot of things that you're familiar with. Here's an example, supervised learning. So I'm going to show you what some of the representations now look like if you do a task that's familiar to you all. It's building these memory hierarchies, but, and here we go. Here's a bunch of data. This is just meant to be an abstract. Assume it's a high-dimensional space, and you've got square kinds of objects, circle kinds of objects, star kinds of objects, existing at different points out in that high-dimensional space. What do you do with an SVM or with a standard neural network? You find a separator that will put all the green circles, if you will, on one side of that separator, right? You have to do that for every category. So if we want to do it for stars, we do it for stars. Each one of those can individually be done, and we know how to do it with, for instance, a supervised network. What does one of our hierarchical algorithms do? What it says is, I don't know from labels. I simply say there's a bunch of similarity-based categories here. So here's a group that all seem to be within a certain region of the input space. Here's another group. Here's another group. Now I can, with a subcortical structure, I can look for labels. I can look for associations in this case, and I can say, which of these categories here are pure with respect to those labels? These ones are, these ones aren't. What do I do when I find an impure category? Just go unsupervised again. So I look within each of these and I say, oh, let's just try, here's a region, here's a region. Now let's check those for purity. Oh, here's a region, here's a region. And eventually I build down the hierarchy just in the places where there are difficult discriminations. The hierarchy is actually very shallow where the discriminations are easy, and it's deep where the discriminations are difficult. Interestingly enough, this is something very much like what SVM does when it's got difficult discriminations to face. And we keep doing this, and what we get is a rich hierarchy, a number of differences between these algorithms. This is discriminative. This one is generative. It's creating versions of the inputs. It's also building a rich hierarchy that's telling you more information than just a discriminative algorithm can. For instance, it's saying, look, there's two different kinds of stars in there. just on the basis of similarity, because these stars live over here in the input space, these stars live over here in the input space. You, the algorithm runner, are telling me that those are related to each other by some label, but I'm also telling you that they are separate from each other, which is interesting. So you now get this much richer kind of representation out. Again, these are published data. Let's compare these two algorithms, just as I said we would. This is just using the one parameter, the branch factor, that is, how many branches will this thing create at each step. And here's chance for a particular set of, this is the Caltech 256 data set. SVMs do very poorly on it, so will we. But this is about the state of the art for this particular data set. And the algorithm will, under all these settings, robustly find roughly the same percent correct. Interestingly enough, the way it will do it, here's the time that it takes the SVM to learn, here's the time that it takes this thing to learn. And the reason is, of course, because it's doing something so much simpler. It's simply finding unsupervised clusters and then looking for purity within them, and then looking for more unsupervised clusters and simply iterating on that. And it only does work where there's a difficult discrimination. Okay, that was all on static inputs, and I promised you I was going to talk about moving inputs, and now the rest of the talk will all be on motion. And so I'm going to introduce a bunch of algorithms that have to do with looking at things changing over time and inferring from the constraints that come from the frame just before, the frames just before, the frames just after, or what happened just before, or what happened just after. So let me look at those. So I'm going to use this as a way of just flying through a bunch of example applications of these. And I'll do some perception, some action. So first perception, I'll do some hearing and then some vision. Hearing, here we go. Oh no, this is where I've got to see if you can hear it.
Blue.
Okay, she said blue, and this is the spectrogram for that, blue, and you can see they're sort of similar, but you can also see they're ridiculously different. And if you just tried to match these two things against each other, which the speech community for ages has tried to do, it's very difficult to do. And an enormous amount of training goes into it. What does the algorithm try to do, the subcortical algorithm try to do? What it tries to do is it says, no, I just want to see a feature, there's a feature, there's a feature, there's a feature, here's a sequence of features or a relation between features. Here's relations between relations. Here's relations between relations between relations between relations. It's building up the recurring relations that occur over and over again every time we hear the word blue. Doesn't need to hear it very many times to build up this little skeleton. Now the matching job is a completely different kind of operation. Because what it's matching now is these skeletons. And it's saying, oh, I think I heard blue. It's not trying to match the raw inputs. Those are gone. So it's lost something. It's doing a lossy kind of compression. But it's also doing compression in a very useful way and using those to recognize. So these are, again, just learned grammatical relations. And the takeaway, if you will, is we're doing iterative partial matching, not trying to take the raw inputs and superpose them or project them or transform them all at once. So we learn speech sounds this way. So it takes in large amounts of text. These are audio books that we feed into it in a couple of different languages. And what it builds are little snippets of speech sounds. It recomposes those using these grammars into longer speech sounds, successions of speech sounds. Here, let me see if I can... and it iterates. Oh, okay. Well, it's going to iterate. Never mind. Yes, yes. Here's the kind. Here, let's listen. Hold on. Put this thing on it. We just wrote things here that seem to be what it sounded like. It's just learning little composites, little elements of the speech streams that it's hearing, and it's putting those together into these trees and using those to do that kind of iterative partial matches that I showed you with the word blue. Interestingly enough, the very same operations are going to work extremely well with a different front end, which I'll briefly show you, for vision. I'm going to skip, I had some slides on static, I'm going to skip those and go straight to moving stuff. And the reason I'm going to do that, of course, is because movies are the real data that you actually get. you hardly ever see a still unless you, I don't know, do computer vision. Otherwise, in real life, you never see one. And furthermore, movies are easier than stills. There are motion cues that help us segment. There's contiguity, which is a form of free supervision. That is, this was over here, now it's over here. Oh, that means those things are probably the same thing, and we can use that to help disambiguate. And structural poses. So, we're just using these simple, motion cues, getting optic flow out of those. And here's an example of why this helps. There's a person in this picture. You can't see him now, but you will. There he is, right? Because he moved. I'll see it again. There you go. It's hard to match up if you have two pictures, this and this. But if I have a movie, I can see the one transform over time very quickly into the other, and it's easy to make the matches. I've got components, this leg versus that leg. When I see the movie, I can see the relationship between those two things and where they articulate. I could see how deformable objects are deforming and keeping certain relations between each other and changing others, and it's building these relations between them. Again, the front end is quite different than it is for sound. In movies, so here's a movie of a dog running, and here's the optic flow for that, and it's easier to show it. Here we go. Now the color is the angle of the optic flow, and the magnitude, the depth is the velocity. So if I show it again, and you can pick out all sorts of things in that. We can then pick out things called superpixels that are the segments, the movement-based segments of the, they don't have to be, but in this case they're movement-based segments, and we can use that to do bounding boxes if we wish. So interestingly enough, we're doing very much the same thing that I did with blue and blue, the same shared back-end mechanism across very different modalities. I can keep doing it. I'll just skip these. Interestingly enough, it doesn't just learn the things we want. So here it's learning, if you want to see, it's learning like this thing, whatever that is, because it sees that over and over again. That thing is, I don't know what you'd call it. We don't have words for it. A puddle or something. I don't know what it is. Here's a bush. It's learning regular things in the inputs, and it's just picking those out because it doesn't know what to look for. So it's just looking at lots and lots and lots of data and finding regularities. So it's building up a large data, an unsupervised data set of what those components look like. All right, and when we want to get supervised information, we do the standard thing, which is we go to the Amazon Wonderful Mechanical Turk and ask people to hand border these things across videos. Okay, let me briefly go to action. I showed you that we are hearing these sounds and we're building little simple motor programs out of them that try to create them. Here is a robot. I don't know if you could see it over here. Can you see it? There's a little bit of motion right over there. When I move its arm, when it then moves, it's seeing some of that same motion, but it's also seeing other things, and it's interleaving action and perception in its representations. It learns to do things. Simple hierarchical reinforcement learning. It's trying to learn to stand up from different positions. Failed there. Yep. And it's going to succeed. Yep. Here. And here is the actual robot doing it. And we go back and forth, by the way, between the virtual versions, which are easy to deal with and train, versus robots, which no adult should ever have to deal with. And so what this guy's doing is just what the virtual guy did. What he's trying what positions he can get to from what other positions. He's not doing yoga. He's finding all the possible positions that are reachable from another position. And again, he's building a big tree of what positions can I get to from what other positions. So he's building representations in which perception and action are interleaved. Okay, now what I want to do is take those kinds of applications and talk about some of the characteristics of them. The key characteristic is this. All those algorithms are intrinsically parallel. None of them are serial algorithms that we have to parallelize. They're intrinsically parallel. They were built out of these components. And that means that they implement well in appropriate hardware. This is important when you build hardware because, as we all know, adding cores doesn't mean speed up. people are talking about Moore's law. We talk about Moore's gap. That is how much you can throw hardware at a problem and not speed things up. And boy, does that happen to all of us every day. So what we're focusing on is Amdahl's law, of course, which is simply saying what kind of software do you have to have, what kind of algorithm do you have to allow throwing hardware at it to help, and what kind of scalability will you get. Inherently serial tasks, you will not get speed up by throwing hardware at it. That's why your quad-core machine isn't 4 times faster than your single-core machine. And inherently parallel algorithms will help. High Amdahl fractions enable direct parallel implementation. So there's a group that has been collaborating with us that's built a bunch of both FPGA and now ASIC implementations of a very highly parallel machine. And they're fabbing these things now with hundreds of thousands of threads that they can run in parallel. Here is an example. This is a simulation that they've run. An example of its watching for its job is to watch the bus. Now you notice this thing, the good one, found the bus right away. Oh, this one just found the bus. Okay, I'm going to go back. There you go. Here it is. Okay, this one found the bus right away. This one's still looking for the bus. It's going to find it. 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 There we go. Okay, so what we're getting is a lot of speed up on tasks of this kind. This is a particular vision algorithm of ours, and you can run the hardware in both low power or high power mode, and we think of that as perching mode, if you will, things that are just watching things for a while versus burst mode where you really care about whatever you're looking at. In just low power mode, you get about a 200x speed up on this algorithm. And just to put that into, so this is not science, this is personal. Here's what I mean. When we were trying to debug this algorithm, we couldn't do it because, and I'm sure that many of you in the audience have had this experience, you can't, it takes too long just to run the buggy algorithm to even find the bug. So you can't, so we had to do, and we have a whole series of publications before all this on GPU accelerations of these things, but of course nobody in their right mind wants to have to write in GPUs. Oops. I mean no harm, but I'm just like, if you don't have to, you don't want to. We didn't want to, but we built them anyway, and we got speed ups just enough so that we could actually make the algorithm work and debug it. What this means in real life is that this task right here goes from 4 hours to 71 seconds. That's what a 200x means. That's, if you will, a difference in kind. That's a difference in my life. It really does make a difference. Scalability of speed and power budgets really matter. They're not just let's build the algorithm and then we'll accelerate it later. They make an enormous difference in can you ever build this algorithm. So we do this kind of thing when we're accelerating robot object. This is the robot just following the ball. This is one who's learning interleaved perception and action just to do a simple task. And again, we don't want to deal with robots if we can help it, so what we do is we're using this wonderful accident, which is the video game people. They came up with these increasingly photorealistic video games. It's almost like they were working for us. And so what you can do is you can train a lot of this stuff on the video game and then use a lot of that to jumpstart training on the robot. So we're training a lot on these video games, and again, what we're doing on the video game is not what typical AIs do in video games. We're only looking at the screen. That's all we see. So we're doing vision processing on this thing. That's the task. It's not about playing the game. Oh, and I don't need the sound, but when I say video realistic, I mean it. We're all waiting for watchdogs. We're trying to transfer this virtual training to robot training. We're having a bit of success on this, so we're looking at objects that it's learned, and it wanders around in a real space and tries to find those objects. Here's an example of that. We've been able to, this is something we do not have an ASIC that sits on top of this drone. Instead, we have to run it remotely, which is awful. If we had that ASIC, here's what we would get, is essentially projected flight time and distance would go up by an order of magnitude, almost 2 orders of magnitude. So that's, just to repeat, scalability of those speed and power budgets makes an enormous difference in the reality of what you can actually build. This is just a demo of that drone. It's in a lab here at Dartmouth, and it's looking for certain things in the world. It's looking for a laptop in this case. I'm just going to show this one example, and then I'll stop. I know it's going to find a laptop. Here it comes. There it goes. Okay. And so it's just searching the world for that. It does it again in that one. Okay. I've iterated a number of principles. This just happens to be the current list of them, but there are several. But they're sort of a surprisingly compact list of things that help us build, constrain the sets of algorithms that we want to build. All these things that I've described are published, and anything that you can't find, you can contact me at our just Dartmouth lab site, which we've oh so cleverly called brainengineering.org. Thank you very much.